Hi everyone. Sorry, I was on mute. Hi everyone. Hello Sonam. Good evening. Hi Ajay. Hello Yash. Okay. So today we are going to solve more questions on SVD, right? I hope I'm audible now. Okay. So basically, as you can see from this slide, that SVD is multi-purpose, right? So like, I mean, some people also call SVD as a Swiss Army knife. So as you can see, it is it is Swiss Army knife, which is having multiple tools. So SVD is actually you will get to realize over the course, okay, over the gate DA course itself. SVD is multi-purpose, okay. It solves many problems. So that's why I'm emphasizing so much on the SVD. Okay. Anyway, so let's just get started. So let's see this question. The left singular vectors of A are the eigenvectors of A transpose A, and right singular vectors are the eigenvectors of A transpose, which means they are saying this U, okay, these are the U's are basically eigenvectors of A transpose A. What do you think? See, if you remember, V's, okay, V's are the eigenvectors of A transpose A, right? These are the eigenvectors of A transpose A. So that's why this statement is actually false. So they are saying that huge are the eigenvectors of A transpose A. So no, right? So huge left singular vectors are not the eigenvectors of A transpose A. So this is false, right? So I can say it is other way around, right? It is other way around. Okay. Now let's just see this question. What they are saying, for any matrix A, the matrices A transpose and A transpose A have the same eigenvalues for any matrix A. So they are saying A A transpose and A transpose A. Do they have all the eigenvalues same? No, right? No. So basically, yes. Yash is saying no, sir. So why that is no? Because only non-zero eigenvalues are same, right? Okay. Now let's just see this. If S is symmetric, then non-zero eigenvalues of S are its singular values. So what they are saying, if S is symmetric, then tell me what is S transpose and what is S transpose S. So I think both are S square, right? Both are S square if S is symmetric. Then basically the singular values are the eigenvalues of S square. So you can say eigenvalues values of S square. Can you say it is just lambda square? Tell me, where lambda is the eigenvalue of S, right? So lambda is eigenvalue of S. Now you tell me, are the singular values just how to calculate the singular values? Square root of this lambda square, right? So if you take the square root of this lambda square, right? By the way, the singular values, as we know, are always greater than zero, right? So basically, it is whatever is this. If it is 9, then the square root will be 3, right? So we don't take the negatives. Okay. So which means let's suppose S eigenvalues are, let's suppose, -3, 2, and maybe you can say -1. In that case, you tell me what are the S singular values if S is symmetric. So it will be, see, the singular value is the square root of the lambda square. So lambda square will be, you can say lambda square will be 9, 4, and 1. So if you take the square roots, it will be 3, 2, and 1. Okay, 3, 2, and 1. So the singular values are always greater than 0. Okay. So that is why it is basically false. Okay. Ultimately, it is false. So you can say that eigenvalue and singular values are actually same. Okay. In the sense, if they are symmetric, then it will be same. But in that case also, it will be the absolute value. Okay. Now let's just see this question. This is question number 14. So what they are trying to say, they are saying if A does not have full rank, full column rank, then 0 is the singular value of A. So basically, generally we don't count them as a singular values. Okay. So I mean, this is a general rule that even if zeros are there, then we don't say these are the singular values. Okay. So so generally, zero is not considered as a singular value. Okay, we will talk about it. Like I mean, why their singular values are taken to be positive. We will talk about it. Okay, don't worry. Okay, we will talk about it. Now let's see this question. What they are saying. Suppose that A is invertible with the singular values sigma 1 to sigma n. Then for C greater than or equal to 0, the singular values of A plus C in are this. So what they are saying that if A is an invertible matrix, which means A inverse exists. So by the way, what is A? If you talk about in terms of singular value decomposition, then this is A, right? What is A plus Ci? It will be some matrix, right? It will be some matrix. Do you think that it will be directly added? You know, the singular value will be directly added to this. So if it is having sigma 1, sigma 2, then will this, will this C, will this matrix will directly added here? Obviously no, right? See, what do I mean to say? That if you have A, okay, if you have A, which is U sigma V transpose, okay. Now, now if I add something here, okay, if I add something here, such that ultimately it becomes U sigma plus IC, okay, INC into V transpose, okay. Let's suppose I add something here such that it becomes this. So which means what I need to add actually, U sigma V transpose, uh U sigma V transpose, and then U INC V transpose, right? So basically, I think this is the quantity, right? This is the quantity that I need to add. So which means what I mean to say, that if you add, okay, if you add U, let's suppose here, okay, if you add U I, let's suppose this quantity U I N C V transpose. Let's suppose you add this, then what will happen? Can you tell me? If you add this, you will take UH common, right? You will take UH common. Just a second. This is not A. Okay. Now it is fine. Now, if you take this, then you will take UH common. And then I think it will be sigma plus INC. And then you will take V trans, which is common, right? So you tell me, let's suppose this is some matrix B. Okay. You tell me what are the singular values of B? If sigma 1, sigma 2, sigma 3 are the singular values of A, then what are the singular values of B? I think this will be sigma 1 plus C, because the singular values are here, right? So this is a diagonal matrix, this is a diagonal matrix. Both are the diagonal matrices, right? So it will be sigma 1 plus C plus comma sigma 2 plus C, like that, right? Sigma 3 plus C and so on. Understood? So these are the singular values of B. Now, if you add this quantity, then it completely makes sense, right? If you add this quantity, it completely makes sense. But if you add, let's suppose just this quantity, okay, just this quantity, will the singular values be this? If you add just this quantity, tell me. In case if you add just this quantity, will the singular values of that particular matrix will be this? Obviously no, right? So if you add this, then obviously it is making sense. They are saying you are adding this. Will this make the singular values, will it directly get added here? No, obviously no, right? So singular values need not to be, obviously, right? Is this okay to everyone? Okay, okay. So that's why it is false, right? That's why it is false. So they are saying that if you add, let's suppose a diagonal matrix here, having all the C's, okay? This is a diagonal matrix having all the C's. Okay, this is a diagonal matrix, C, 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 like this, right? Sorry, 1 plus C. Uh, no, okay, sorry. This is only C. So if you have diagonal matrix, if you add directly, then obviously the singular values won't be directly added, right? So that's why it is false. Okay. The right singular vectors of A are orthogonal to null space of A. So what they are saying, that right singular vectors. So what are the singular vectors? Basically, we call only till sigma r we call them singular vectors. Okay, v1, v2. So these are the right singular vectors. Tell me, are they orthogonal to null space of A? See, these are in the null space of A, right? This is in null space of A. Are these vectors orthogonal to null space of A? I think yes, right? Obviously, these are the orthogonal to null space of A. So that is true. Okay, cool. So I hope this is easy question. I hope you understood, right? Okay, let's solve this question. So what they are saying? They are saying that let S be a symmetric matrix with eigenvalues lambda 1 to lambda n, countered with the multiplicity, which means that if it is repeating twice, they are saying, okay, I mean, they're writing it twice. Okay. So that's what they are saying. Order the eigenvalues so that, okay, in this order, and then that's okay. Be the orthonormal eigenbasis. Eigenbasis means a basis of eigenvectors. Okay. Eigenbasis might be a new term to you, but it is actually, very easy to understand. It is a basis consisting only eigenvectors. First of all, tell me, do you think eigenbases always exist? Do you think eigenbases always exist? What do you think? Eigenbases always exist for any matrix? See, what is eigenbasis? A basis consisting only the eigenvectors, right? A basis consisting always exists for obviously for the square matrix I'm talking about. Okay, so here always exist for square matrices. A basis consisting the eigenvectors. Understood? Right? Now you tell me, do eigenbases always exist? What do you think? Do you always have a basis consisting eigenvectors? Obviously no, right? Obviously no. Possible only when the eigenvectors are linearly, just tell me, linearly independent, right? So possible only when eigenvectors are linearly independent, right? Okay. Now you see this. So what they're saying here, they are saying that order the eigenvalues so that this let since it is a symmetric matrix, first of all, tell me, do you think eigenbases exist? Right? For the symmetric matrix, obviously eigenbases exist. Okay. Now what they're saying that let this be the orthogonal eigenbasis. Okay. So they are saying that this is a orthogonal. Okay. So this is the orthogonal eigenbasis. Now what they're saying that where these are the vi has the eigenvalue lambda I. Okay. Show that. So they have given. Okay. They are saying that okay all the eigenvectors are orthogonal. Now show that the singular values of S are this. Okay, in particular, rank of S is R. So can you show if it is symmetric matrix, then the singular values are basically the absolute values of the eigenvalues, right? And the singular values obviously they're taking till greater than zero. So we can show it. In fact, I will show. Okay, don't worry. And here AM and GM are equal. So basically, number of the eigenvalues non-zero are R. So rank is also R in case of symmetric matrix. Okay, this is only where then the matrix is symmetric. And how we can prove it? The other way of proving it is basically here. Okay, so basically okay, let's just do one thing. Let's just do step by step. Let's just first show the symmetric for the symmetric matrix, the singular values are this. Okay, and then in the next step, what they're saying, find the singular value decomposition of S in the outer vector form. Okay, we will do it. So first, let's just show that singular values are lambda one, lambda two, like that till lambda r. Right? Singular values are this. Okay. So how to do it? See, singular values are nothing but eigenvalues of S transpose S or SS transpose doesn't really matter. Okay. I mean, the non-zero singular values, you can take either eigenvalues of this or SS transpose doesn't really matter. In each case, anyway, in this case, it is actually S square if S is symmetric, right? So S square eigenvalues will be lambda 1, lambda 2 square till lambda R square, and maybe even zeros are there. Okay. Maybe some more zeros are there, right? I mean, see, till till lambda r, I'm assuming it is greater than zero, and remaining are, let's suppose it is zero. Okay, so remaining are zero. Now these are the eigenvalues of this. So what are the singular values? Notice lambda square. Eigenvalues of this s square are lambda square, right? If eigenvalue, so it is not even related to SVD. It is a general thing that eigenvalues of S are lambda, then eigenvalue of S square are lambda square, eigenvalues of S cube are lambda cube, like that, right? Okay. Now, if these are the eigenvalues of S square, then what are the singular values? Singular values will be just square root of this. So, uh, do you know this? That let me ask you one thing. Do you know this? That let's suppose I ask you square root of 9. Will it be plus minus 3 or just plus 3 or just minus 3? Which one is correct? Square root of 9. Let's suppose it is A, B, C. Which one is correct? What do you think? Okay. Ajay is saying B. Anyone else? Just let me know. What do you think? Okay, just have a random guess. And this need not to be, the perfect answer. Just try it out. What do you think? Okay. Bachu Paul is also saying B. So anyone else wants to try? Okay, Sonam is also saying B. Okay, that's great. I think most of you are saying B. So should I need to explain this? C. C. A square root function is always positive. Okay, this function always returns positive. So for example, if I just ask you, then I just cancel it out. Then I just say that okay, this is -3. Is this true or false? This is true or false? If it is false, then the false is in this step number one, or in the step number two. Okay, where is the fault? Where is the fault? Yes. So 9 you can definitely write -3 square. That's not an issue. But you just can't just cancel out. Okay. It will be a huge problem. Okay. You can anyway write the negative number. It doesn't mean that you are getting the negative number here. Okay. So basically, whenever you are canceling out, then you need to make sure that inside must be positive. Okay. If you don't want to make sure this, then in general, you can say square root of x square is mod of x. Okay. This is correct. Okay. Is this always correct for any number x? Okay. Tell me, for any number x, is this correct? For any number x, this is wrong. So basically, if I just say, tell me if it is true or false. This is this is true. Okay. And just tell me for any x, this is true or false? For any x, for just let me know. Let's suppose this is A, this is B, this is C, this is D. You can just tell me which of the following is true. Okay. So I think ACD. I think Yash, Ajay, Sonam, everyone is saying ACD. Let's just check it. Okay, let's just check it. So A is saying that okay, if X is positive, you can definitely take it out. So that's true. If if you say for any X, can you take it out? No, that's false, right? For any X, can you take it out and take the mod X? Yeah, that is true. For negative, you can take it out and it will be mod X, right? So these all are true. So basically, what I'm trying to say here is that here in this particular case, if you have 9 equal to something like this, if you have this, then uh this -3 square, you can't just write like this. Okay, you can't write like this. Okay, this is wrong. So basically, if you have for example, these are the singular values, sorry, these are the eigenvalues of S transpose S. So let's suppose lambda 1 square is the eigenvalue of S transpose S. Then a square root of lambda 1 square is singular value of S, which is nothing but mod lambda 1, right? It is mod lambda 1. Okay, is this okay to everyone? It is like you're not doing any favor to this or something like that. It is a mathematics. Okay, if you have inside the square root, if you have lambda 1 square, then outside you will be writing mod of lambda 1. Okay, cool. So I think that is okay to everyone. Now, let's just see that what they are asking. So we have shown, right? We have shown that the eigenvalues, sorry, the singular values will be this. Now let's just see that why the rank is this. Okay. So why the rank of S, rank of S will be R. Okay. Why? If S is symmetric, sorry, symmetric and eigenvalues of S are lambda 1, lambda 2, lambda R. Okay. These are the eigenvalues of S. Maybe you can have zeros. So, what is the one of the argument? Okay, so argument number one. Okay, or you can say method one to prove it. Method one. Let me just say without introducing singular values. So what you can say is that number of non-zero eigenvalues, or maybe you can say number of zero eigenvalues are basically n minus r. So nullity is n minus r, right? Because every eigenvalue will be giving you, one linearly independent vector. So number of, you can say, zero eigenvalues are n minus r, which is equal to nullity since S is symmetric. Okay, understood? Okay, rank of S is non-zero eigenvalues only if it is symmetric. So basically, number of zeros eigenvalues are n minus r. It is as good as nullity only if S is symmetric. Suppose S is not symmetric, then if this is n minus r, then nullity will be at most n minus r. Okay, at most, but which means you can say it is greater than equal to nullity. Okay, so at most nullity could be n minus r, but for the symmetric matrix this is equal, because for the symmetric matrix every zero, okay, for every zero, let's suppose there are n minus r zeros, every zero will give you one linearly independent vector, which is a solution of, basically you can say, ax equal to 0, and I mean the number of vectors in the null space. Okay, so basically just because it is symmetric, that is why that is the case, and nullity is this. So that is why you can say rank is. Now what is the method 2? What is the method 2 where we can introduce singular values? What is the method 2? Tell me. See, uh, as you know, the singular values, right? Eigenvalues of symmetric matrix. Eigenvalues of symmetric matrix. Lambda 1, lambda 2, lambda 3. Till let's suppose, I mean non-zero eigenvalues I'm writing, lambda r, okay? I mean these are the non-zeros. Okay. Then what are the singular values? That's what we have just proved, isn't it? Is this okay to everyone? And number of singular values for any matrix doesn't really matter. Okay, doesn't really matter whether it is a symmetric matrix or not. So number of singular values. I mean, specifically, some people write it non-zero, but actually zeros we don't count. Okay, but specifically, if you want, you can write it non-zero. Number of singular values is exactly equal to rank, which is R, right? And that is true for any matrix. For any matrix. So that's how you can also prove. Okay. So in this method too, where we have used a symmetricity property, can anyone tell me? Let's suppose, this is step one from going from here to here. This is step two. Okay. Tell me in which step I have used symmetricity property. In the step one, right? Why? Because eigenvalues and singular values are having this kind of relationship that is true only for only for the symmetric, right? So for, is this okay to everyone? Okay. Now, okay, sorry. I think there was a second question here. So the second question is saying find the singular value decomposition in outer product form. Do you remember outer product form? How many of you remember outer product form? Anyone? I mean, at least, do you remember that we have talked about it? Because that is going to be there in the quiz. Okay. So if you don't don't remember, then you should actually, because in the quiz I have put multiple questions regarding it. Okay. So actually, let me just remind you. See, we write A as U sigma V transpose, right? Now, sigma is anyway, like, I mean, these are the diagonal matrix of scalars. So basically, you can consider that generally we do row into column. Okay. But let's just do column of U, which means this is U1, right? Till UM. Let's just do column of U, and these are the sigma. So let's suppose this is, you can, I think, multiply here, or maybe you can multiply uh, these sigmas, and either in U or in V doesn't really matter. So let's just suppose this is V1 transpose, right? Like this, okay? So the sigmas, you can multiply, I think, anywhere, right? So maybe let's just suppose this is sigma 1, this is sigma 2, V2 transpose, and so on, right? And if they're sigma r only, and after that it is zero, let's suppose. So basically, what you can do, you can multiply this column and this row. And if you multiply this column and this row, this is called outer product. And it will be a matrix itself, right? So it will be U1 or maybe sigma 1, U1, V1 transpose plus sigma 2. This is a matrix. This is again a matrix, sigma 2, U2, V2 transpose, right? Plus, and so on, sigma r, UR, UR, VR transpose, right? Is this okay to everyone? Now, what they're saying, find the singular value decomposition of S in the outer product in the terms of lambda I. Okay, so these are the lambda I. I mean, sigma 1 is modulus of lambda I and VI. Okay, so that's interesting. Let's just first find out, you know, VI are the orthogonal bases, right? So let's just first find out the singular value decomposition of A in terms of VI only. In terms of VI only. So you know that eigenvalue decomposition. Let me write. Okay, eigenvalue decomposition. or maybe directly let me write singular value decomposition. Tell me what are the eigenvectors of S transpose or S transpose S, which means this is also S square, this is also S square. What are the eigenvectors of this? Tell me. Yeah. So the eigenvectors are same, right? Eigenvectors are same as S, right? So which means if we have the eigenvectors of this, then uh you can directly write that suppose these are the eigenvectors, the singular value you can directly write the SVD, right? So what is the SVD? SVD will look something like this. Okay. So this is you can say modulus of lambda 1, modulus of lambda 2, right? And so on. And then this is basically V1 transpose, V2 transpose, like that, right? Okay. Let me know if it is okay to everyone. Okay. So what is the what is the outer product sum? Instead of U1, you will be writing V1, right? That's the only difference. And tell me what is the V1 into V1 transpose? If it is unit vector, then it will be one. But I think these are not the eigenvectors are not the unit vector here, right? Okay, so that's fine. So instead of U, you can write V. So which means it will be something like this, right? So the right singular vectors are basically, so actually there are multiple SVDs. So either you write plus or you write minus. I don't think it will really matter. I think yesterday also we were arguing on the same. Okay. So there is a small topic which is remaining, uniqueness of the SVD. Basically there are you can always replace. Okay. For example, if A is U sigma V transpose, then you can always replace this U and this V transpose. Okay. Also by minus U and minus V, because the reason is that if x is eigenvector of something, okay, maybe a transpose x, a transpose a, or anything, then minus x, in fact kx is also the eigenvector. But if you take any other multiple instead of minus one, will it be the length will be just one? Tell me, if u1 is having length as 1, then 2u1 will be having length as 2, right? But minus of u1 will be having length as same. So basically, you can always take minus. So we will talk about it, that there are no unique SVDs. There are multiple SVDs that can exist. Okay. So that's why they are writing plus minus. Anyway, so we will talk about the uniqueness of the SVD. So I hope this particular outer product is fine to everyone. So instead of U, we will be writing just V. Okay, V1, V2, like that. Now let's see this. Show that now they are saying that uh, possesses the same non-zero eigenvalues. Tell me. How to show that? I think we have already proved, right? Yes. So in one of the lecture, we have already proved that AB and BA share same non-zero eigenvalues, right? And how we have shown it was also very easy, right? So maybe you can watch that lecture again. This is a small lecture. Can you watch that lecture? It is a small lecture. I think in 5-10 minutes you can just rewatch, right? So you can just multiply. Yeah. So let me probably, if you want, I can just do it. So suppose that AB has eigenvector, eigenvalue lambda, and eigenvector. x. Okay. Which means abx equal to lambda x, right? Let's suppose this. Now what we can do, we can multiply both side. Okay, let's suppose we multiply both side b. Then what you will do, this will be ba into bx, right? Bx equal to b lambda x, right? Then this will be ba bx equal to bx equal to, you can write it lambda into bx. Okay. So you can say BA is having different eigenvector, which is Bx, but the eigenvalue is same, right? This is lambda, which is same. Okay. So eigenvalues are actually same. So this is also the eigenvalue of B. Now just tell me what guarantees that lambda, this eigenvalue should be non-zero. So I am saying that only non-zero eigenvalues are same. Only non-zero eigenvalues are same. Why that is the case? Because why I am guaranteeing that only non-zero are same? The reason is that see, since x is eigenvector, right? That is why x is non-zero by definition. Do you remember this? Do you remember that eigenvectors cannot be zero? Eigenvalue can be zero, but eigenvectors cannot be zero, right? I mean, this is by definition, right? So basically, what you are saying here, that if x is non-zero, right? If x is non-zero, then tell me, let's suppose lambda is also non-zero. Then lambda x is non-zero. Or maybe let's just do one thing. If x is non-zero, so basically I want to prove that only non-zero eigenvalues are shared. Can anyone help me to prove this? That only non-zero eigenvalues are shared. I mean, if lambda is zero, then we can't guarantee it is shared. So basically, here we are saying that bx, this bx is eigenvector, right? But can we directly say it is the eigenvector? Bx is the eigenvector? No. So basically, we can claim only when bx is not zero, right? Non-zero. Only when we can say that lambda is eigenvalue and so on. So bx, if I'm claiming that bx is non-zero, then only I can say that lambda is eigenvalue. Okay. I mean, then only I can say that bx is eigenvector. So to prove that bx is non-zero, okay, to guarantee that bx is non-zero, we have to make sure that lambda is not zero. Why? Because see, this was abx equal to lambda x, right? You multiplied b both sides, it was something like this. Okay. Now we are saying that this bx, this particular bx, is eigenvector. We are saying it is eigenvector, right? So to make sure it is eigenvector, first step is that we need to make sure that bx is non-zero. Non-zero. Need to make sure this, right? Need to make sure this. Then only we can claim further that it is eigenvector. Then the further claim is bx is eigenvector and lambda is eigenvalue. Okay. This is the further claim. Now, as you see here, that this was given to you. Now, to make sure that bx is non-zero, right? We need to make sure bx is non-zero. Then only we can do this. So see here that x was the eigenvector, right? X is eigenvector. This is given to us, right? Which is obviously non-zero. Then assume, okay? Assume, here I'm assume lambda is not zero. Okay. It means lambda x not equal to zero. If lambda x is not zero, then can be the bx zero? See, if bx is zero, then lambda x will be this particular, obviously this whole thing will be zero, right? Then lambda x will be anyway zero. So So if it is non-zero, then bx has to be non-zero. Okay. So for this lambda not equal to zero only, we are able to make sure that bx is non-zero. Okay, so that is why lambda is basically the non-zero values. Okay, non-zero eigenvalues. I mean the shared eigenvalues are non-zero eigenvalues. Anyway, this was already told in one of the lecture. You can definitely see this lecture. In this lecture, we have already covered this particular concept. So the lecture name is 10D, relationship between eigenvalues and eigenvalues of AB and BA. A concept asked many times in the interview. You might be you might remember that I have shared this particular one particular question of one interview, right? Just 2 3 days back also. In one of the interview also in ISC CDS, they have asked this question that what is the relationship between AB eigenvalues of AB and BA. How many of you seen that particular post that I posted? In ISC CDS interview, they've asked this question, right? Okay. Okay. Actually, this is very popular. Okay, this is very popular question. That what is the relationship between the eigenvalues of AB and BA, right? And it is very much needed to SVD also. So anyway, like you can see this. So that's how we can prove that AB and BA, or maybe you can take A transpose A and AA transpose or whatever, right? So BA and AB, these things, right? Okay. So here also they have proved in the similar way. Here AB is not zero. So yeah, AB is not zero, which means this if we are assuming this eigenvector, since if AB equal to zero, then I mean they have proved in some other way, but that's fine. Okay. Now let's just see this particular question. What is the rank of this matrix say? Can you just calculate this question? Can you just let me know what is the answer? So from here, number of non-zero singular values, right? 2, 1. So rank is 2. Rank is 2. The eigenvalues of A transpose A are eigenvalues of A transpose A. Do you need to find A transpose A? These are the singular values, right? Eigenvalues must be the square of this, right? The square of this. Okay. So it will be, I mean, you can see the dimension. I think the dimension will be A transpose A. So this is 2 cross 3. Then A dimension is 3 cross 2. So A transpose A will be 3 cross 3. This is 3 cross 3. This is 2 cross 2, right? Now you tell me the eigenvalues here. It will be 4, 1, and 0 because this is 3 cross 3. This is just 4 and 1, right? A non-zero eigenvector of A transpose A is non-zero eigenvector of A transpose A, they are asking. I mean, eigenvector is anyway non-zero, so don't worry about it. So should we be taking the column or should we take the row? Yes. So any row, okay, any row of B transpose. Okay. So these are the answers here, right? Now let's just see this. Which of the following are the true statement about the singular value decomposition? All eigenvalues lambda of A transpose are identical to each other, are the same in this particular case. So this is upper triangle matrix. Okay, just solve. I mean, just think about it. Yes is saying the eigenvalues are 941 or something like this. So if you take A transpose, so what is the A transpose here? All zeros. 1 0, 0 0, 0 2, 0 0, 0 0, 3 0. Right? Okay. So it will be this row multiplied by this row. I think it will be just 1. This row multiplied by this row. I think it will be just 0. And all the things will be 0, right? Okay. Now this row multiplied by this is 0. This row multiplied by this row is 4. And then all are 0. Okay. So this row multiplied by this 0, 0. It will be, I think, 9. And then 0. And then 0, 0, 0, 0. Okay. So this is AA transpose. Now you tell me, are the eigenvalues are 149? Yes. So are they identical? Obviously no, right? So I think no. What about others? Non-zero singular values. Just let me know. Okay. So non-zero singular values, yes, right? That is true because it will be, 1, 2, and 3, right? This is yes. Removing the last row of A doesn't change the non-zero singular values. Okay. So if you remove the last row, okay, which means you are removing this, which means basically you are saying this is okay, this is 9. You are removing this, you are removing this. So what do you think? Yes, it is also true, right? It seems it is true. So I think 2 and 3 are true. So the answer is B. Okay. Let's just see this question. So what they're saying here is that which of the following statement about the singular value decomposition is true when written in this form? So the sigma one is a singular value, u1 is left singular vector, and b1 is the right singular vector, right? Assume that all sigma is are the singular values and non-zero. Okay. So tell me, is this orthonormal basis for the column space? Is this in the column space? Yes, right. So that is true. What else? The singular values. Which of the following statement? So you can consider this as MSQ. The singular values sigma I are the real numbers of arbitrary sign. No, right? So real numbers of arbitrary sign means okay. So are can they be negative? So basically, can they be negative? So that's false. The SVD separate a rank R matrix A into sum of R minus one rank one matrices. Is this R minus one? No. SVD of matrix A is unique. I will talk about it, but it is not actually. So I think A is the only answer, right? Okay, A is the only answer. Okay, SVD is not unique. Now let's just see this question number 22. How many non-zero singular values of the following matrix A have? Okay, so you can I think compute it. 1, 2, 3, 4, 5, 1, 2, 3, 4, and 1. This is 2, 4, 6, 8, and 2. Okay. So the columns are I think linearly independent to each other. As far as I can see, maybe okay. Uh, I mean they are not multiple of each other at least, but anyway. So how many non-zero singular values they are asking? So I think we need to calculate it, right? We need to calculate the rank of A. Okay. So I think you can do it. See, this is multiple of this, this is multiple of this is multiple of this. So anyway, these are zeros. And then this is 112, this is 512. I think it's seeming to be 2, right? Rank is seeming to be 2. So most probably C is the answer. Okay. This is a rank 2 matrix because the third column is linearly dependent, or maybe you can understand with the rows also, right? These three rows are linearly dependent, so these three rows are redundant, and then only two rows are remaining, right? Okay. Now let's just see this. Which of the following are true about the singular value decomposition? If a square matrix Q is orthogonal, then its singular values are 1. What do you think? See, if it is orthogonal, sorry, orthonormal, then what is this SVD? The same matrix, then identity matrix itself, right? This is one of the SVD. Any other SVD can you suggest me? Any other SVD? Maybe you can uh if you try to put QH last, then will it be? I think yes, right? Okay. So yes. So if you try to put QH last, yes, this will be one more SVD because this is also the orthonormal matrix. So ultimately we want one orthonormal, right? One diagonal, one orthonormal. So yes, that it is also satisfying the condition. One orthonormal, one diagonal, one orthonormal. This is also satisfying the condition. So these are the just two SVDs, right? And in both of the SVD, you can see that okay, eigenvalues are sorry, the singular values are ones. So that is true. A matrix with since it is by the way, since it is square matrix, so that's why I mean you will be having this identity in the between, right, which is also square. A matrix with rank r will have exactly r singular values greater than 0. I think this is also true, right? Every real matrix has an SVD. Yes, this is also true. So I think 1 2 3, right? Okay, let's talk about it. So what they're saying, for each of the following statement, mark whether they're true or false. For a matrix A in the single value decomposition, the factor u is an orthonormal matrix. A factor u, this is orthonormal. Tell me this is true or false? In the SVD, this is orthogonal matrix. Yeah, this is true, right? This is true. If the determinant of A square is 1, then A's eigenvalue must be 1 or minus 1. So it means that determinant of A square is 1, then determinant of A is basically, you can say it could be plus minus 1, right? Now, eigenvalue need. I mean, is this necessarily true that eigenvalues are plus one or minus one? It is not. It need not to be, right. One could be 1/2, another one could be 2, something like this, right? So, for example, if the eigenvalues are this 1/2, 2, then also the determinant will be 1, and then also the determinant of A square will be 1, right? So, I think this is false. This is true. For a symmetric, okay, just ignore this PSD. Okay, we will talk about it. The positive symmetric definite PSD or symmetric positive definite. These matrices we will talk about. Actually, their eigenvalues are greater than or equal to 0. So we will talk about it. We will talk about it later. Okay, what are the PSDs? Let's just see this particular question. A 5 cross 5 matrix has eigenvalues lambda equal to 3 of algebraic multiplicity 5. So which means they are saying that 3 is repeating 5 times and geometric multiplicity 1. Okay. And the matrix B is therefore diagonalizable. Is this possible? If it is 5 cross 5 and geometric multiplicity is just 1, it is not possible, right? Not possible. Eigenvectors must be linearly independent. Yes. That's really great to see that every one of you are actually answering very correctly. It is a very good moment for me as an instructor also, that I mean all the things are getting correctly delivered. So let me just capture this. All the eigenvalues of real symmetric matrix are real. Yes, right. I mean, this is the property. So this is true, and this was false. This is true, false, true, false, true. So let's just check true, false. Okay, true, false, true. Right. Okay. Let's see this. Show that the singular values of orthogonal matrices are equal to one. I think we have just shown it, right? Singular values are one. We have just shown it using two SVDs, Q, I, Q, right? Using these two SVDs, we have shown. Okay. Let let A be this matrix and Q1 be M cross M orthogonal and Q2 be N cross N orthogonal. Show that A is same singular values as Q1 A Q1. Okay. So they are saying that orthogonal. Okay. So A is M cross N. There is some Q1 which is M cross N. Q2 is N cross N. Okay. So that A has same singular values as Q1 A Q2. Q1 A Q2. It's very easy, I think, right? Okay. So yeah. So Ajay is saying orthogonal matrices preserve length. Right. So okay. So how it is directly applicable here? Yes, I got your point. But basically, I mean, any change, or let me just simplify it first. Okay, and then we can talk about the geometric multiplicity. So let's suppose A is having some singular values which are sigma, right? So what are the singular values of this? U sigma V transpose, and then Q1, and then this is Q2, right? Okay. Will this be a orthonormal matrix? If Q1 and Q are orthonormal, then their multiplication is also orthonormal. What do you think? So I need to find the singular values of Q1 A Q2. So there are actually, I mean, geometric ways also. So I think okay, they are doing in this way. So basically they're finding A transpose A, and it is coming out to be has the same eigenvalues of A transpose A. Okay. Oh, that's really nice. So basically, what they are doing, they're finding out A transpose A, right? I mean, this transpose this. So they're getting that this transpose this is coming out to be Q2 transpose A and Q2. So this eigenvalues of this and A transpose A are same. How you can identify it? Because these are the similar matrices. So this is same as, right? So this is similar to A transpose A. And similar matrices has the same eigenvalues. So that is why these two are basically having the same eigenvalues, right? Which means the singular values will be same. Okay. And what is the other way, which is geometric way? What is the other way? You can think in this way also that if you multiply any vector by A, right? Then then basically what it will do, it will it will change, okay, the value, or it will scale the values proportional to the sigmas, right? Sigma 1 x1, do you remember? Sigma 2 x2, like this, right? I mean, it will change the values proportional to sigma. Now will this also not do the same thing? It cannot change its length. It cannot change the length. It cannot also change the length, right? So Yash is saying Q1 and Q2 are orthonormal. Yeah, that's why I'm saying it cannot change the length. It cannot also change the length. The only factor here which can change the length is basically sigma. So this will also be changing the length in the similar proportion that it is changing, right? So which means it will change in the proportion of sigmas. So this will also change in the proportion of sigmas, right? Okay. Anyway, you can understand this way also, right? So basically, A transpose A, you just find out the this matrix transpose this matrix, and then see that okay, the eigenvalues of this is same as eigenvalues of A transpose A. So that's why the singular values will also be the same. Okay. Is this understood to everyone? That why the eigenvalues are same? So basically, let's suppose this is B, and I want to prove that singular values of B and A are same. So which means singular values of B is nothing but eigenvalues of B transpose B. And singular values of A is nothing but eigenvalues of A transpose A. I mean, in square root of these values, right? So the eigenvalues of B transpose B and eigenvalues of A transpose A are actually same because they are similar matrices. Okay. Now let's just see this question. Tell me, what is this A transpose UI? See, A into, as you know, V equal to sigma A into Vi equal to sigma A into Ui, right? You know this. Now, what is A equal to, if A is U sigma V transpose, then A transpose equal to V sigma transpose U transpose, isn't it? Sigma transpose and sigma will be same. I mean, it will be anyway diagonal matrix only, right? Okay. Now you tell me A into Vi, which means A into these vectors. So similarly, A transpose into Ui will be what? Sigma I into, it will be this vector, right? So which is Vi. So what is correct here? A transpose into Ui equal to sigma I into Vi. So I think B is correct, right? Uh yeah. Okay. Understood. Okay. Now let's just see this question. Let sigma be 2 cross 2 matrix with the eigenvalues this and this. Give an expression for sigma. Okay. So with the eigenvalues b1 equal to this, with the eigenvalues b1 equal to this, with the eigenvalues 3. Okay, so b1 has the corresponding eigenvalues 3, b2 has the corresponding eigenvalues 2. So can you write the expression for sigma? So which means they are saying sigma into b1 equal to 3b1, sigma into b2, they are saying 2b2, right? Let sigma power 1 by 2 be the matrix such that sigma power 1 by 2 into sigma equal to sigma. Give an expression for, do not try to simplify your expression. Okay, first tell me what is the sigma. So basically, uh, you can see that sigma uh, is a matrix which is a square matrix, by the way. So you can write, if you have two independent, linearly independent eigenvectors, then you can write sigma into eigenvector set of eigenvectors equal to uh, lambda, which is 3 and 2, and then u. So basically, we need to find sigma, right? So sigma will be, you can say it will be u inverse u, basically, yes, sigma u equal to lambda u. So now, sorry, it will be u lambda. So now it will be u lambda u inverse. Now, since you can notice one thing is that these are not just eigenvectors, these are the orthogonal eigenvectors, right? So u inverse and u transpose are same, right? So which means u transpose. So you can find out sigma like this. Okay, you can find out sigma like this. Okay. Now what they're saying, they're next saying that let's just denote some notation. Sigma power 1 by 2 is a metric such that sigma power 1 by 2 into sigma power 1 by 2 is giving you sigma. Or maybe if you are confused, let's just say it is x. So x into x is actually sigma, or x square is sigma. Then what is this x? That's what they're asking. What are the two matrices that are making you? What are the two? I mean, you can say the same matrices, okay? Not any two random matrices, two same matrices. Yes is saying eigenvalues will be root of the eigenvalue, but eigenvector will remain same. Okay. Anyone else? So let me write what Yash is saying. So Yash is saying that if we are finding the square root of the sigma, right? Any power of the sigma will be basically having the same eigenvectors, but the eigenvalue will be changed. So which means you can also find out sigma power 1 by 2 similarly as this. Okay. Uh it will be it will be basically the eigenvectors will be same. Okay. And then the eigenvalues, which will be instead of 3 and 2, it will be square root of 3 and square root of 2. Okay. These will be the eigenvalues, right? And the eigenvectors will be same. So these matrices will be same, but the eigenvalues will be different. Okay. So now let's just see this. This is a little long question. Let me see what they're saying. We want to compute, okay, this SVD of the matrix. One way to compute SVD by the hand and exploit the relationship between singular values x and the eigenvalues of the related symmetric matrix. What symmetric matrix eigenvalues are related? I think they're just asking you to find out the SVD. So maybe you can find out x transpose and then find out what are the eigenvalues and then singular values. Okay. What is the relationship between the singular values of x and eigenvalues of the symmetric matrix? These are the square root relationship that we know. Generalize for any matrix Z, not just x. What symmetric matrix has the eigenvalue related to the singular values of x? Prove that every singular value of Z can be identified by looking at the eigenvalues of the matrix. Yeah, this is just a square root, right? So the singular values of Z are the square root of this, right? I mean, this is okay. So these are just definitions. Okay. Let's just see this question. Prove that if A is a real matrix such that it is a symmetric also, okay, it is a symmetric matrix, then the singular values of A and the absolute values of uh, the eigenvalues of A, then the singular values of A, I think, okay, this is a repeated question, I think, okay. This is a repeated question. By the way, like maybe I might have taken the earlier question from some other university. So this question I have taken from Stanford. Okay. So they are saying let A be such that rank of A is M with the singular values of this. Okay, A is this. Determine the singular values decomposition of the matrix as this. So you need to find the SVD of this, these matrices in terms of the singular value decomposition of A. Use the orthogonality whenever possible. So basically, they are saying if the singular value decomposition of A is given, then can you find out the singular value decomposition of A transpose A inverse and these things? Do you want to try it out? Just find out the singular value decomposition of A transpose A inverse. And then multiply by A transpose and some other variants. So basically, you can find out this A transpose A. If A is given, then you can find out A transpose A, and then you can put an inverse on this. So you can just, it is just a calculation based question. For example, A transpose A will be this, right? And this you have written in terms of SVD, and then you take inverse of this, and then you will be finding out A transpose A inverse like this. Similarly, A transpose A inverse multiplied by A transpose also. Okay, so you can just solve this question. You just try this question and see your answers are matching or not. Okay, try and see if answers are matching. Okay, cool. So this is, a few questions we have solved regarding the SVD. Now, little bit idea. Okay, most of the idea you must have got regarding the SVD. Now we will have one quiz of 20 questions, and then for the quiz, just revise all the questions for all the concept of SVD, because the quiz will be little interesting. So that's why I just urge you to just revise all the concept of the SVD and just attempt that quiz. Okay. After the quiz, actually, the all the concept, everything about the SVD will be much more clear. Okay. Cool. So if there is any doubt, you can just let me know. Yes. Yash is asking why they involve P in A transpose A inverse answer. Okay. This is A transpose A inverse. Since the singular values are currently in the ascending order as opposed to descending, we therefore will P with the matrix with the ones in the antidiagonal and 0, 0, which is clearly. Okay, so basically they're defining a matrix P, which is P square is identity. So they are just multiplying by the identity, and then they are doing something like this. So probably they are making sure that ultimately the eigenvalues will be I mean the final this P into sigma transpose sigma inverse into P. Basically, this is actually the diagonal of this. Okay, so they're, I think they're just reversing this the order, because earlier it might be, okay, in the sigma transpose sigma, it might be sigma 1 square, and then 1 upon sigma 1 square might be the lowest value, right? If sigma 1 square is the highest value, then 1 upon sigma 1 square is the lowest value, and then they want it to be on the last. So basically, if you multiply this P and P, okay, P and P two times, such that P is defined like this, then it will be actually on the last. So here this is actually sigma 1, 1 upon sigma 1 square, 1 upon sigma 2 square. This is like this, right? But if you write like this, then actually they're reversing the order. Okay. It is a very smart trick that they've played to reverse the order. Okay. Okay. Yeah. Thank you, everyone.